Los Alamos cafeteria. Some of the smartest people on Earth are walking to lunch. Edward Teller, Emil Konopinski, Herbert York. They're talking about flying saucers. Whether aliens could break the speed of light. Stuff like that. And then one of them just stops mid-bite of his sandwich, and he asks a question that's been haunting us ever since. Where is everybody? That was Enrico Fermi, and what he'd just done wasn't just ask a weird lunch question. He'd opened a door we still can't close. Because here's the thing. The galaxy is old, really old. Hundreds of billions of stars. The math says aliens should be everywhere. So why haven't they shown up? Today I'm going to tell you the answer. And it's not what you think. Let me be clear about what we're actually talking about. This isn't about whether aliens exist. Maybe they do. Maybe they don't. I don't know. You don't know. What I'm saying is way more specific. Even if there are millions of civilizations out there right now, they're never coming here. And we're never going there. Not because they're not smart enough, not because they don't want to, but because of something way more fundamental. Okay, so the Milky Way, about 10 billion years old, 100 light years across, somewhere between 200 and 400 billion stars. Now, Fermi did this napkin calculation back in 1950. He said, what if just one civilization developed spaceflight? Even slow rockets, nothing fancy. They could reach the nearest star in maybe 10 years. Then they spread outward, star by star. How long would it take to colonize the entire galaxy? His answer. Maybe 10 million years, maybe 100 million if they're taking their time. Now, pause for a second. 100 million years sounds like forever to us. But the galaxy's been around for 10 billion years. That's 100 times longer. So if any civilization started this process, even a billion years ago, they should be everywhere by now. Including here. They should have gotten here a long time ago. So, where is everybody? That's the Fermi Paradox. Fermi never called it that himself, but it's one of the most haunting questions in science. Here's where the sci-fi dream starts falling apart. The problem, the real problem, is just space. The emptiness. People don't get how far apart things actually are. They really don't. Let me give you some perspective. The nearest star to us, not the sun, but the next one. It's called Proxima Centauri, about 24 light years away. What does that even mean? Light travels at 186,000 miles per second. That's fast. Nothing goes faster than that. And even at that insane speed, it takes over 4 years to get there. Now, we've built some pretty fast spacecraft. The fastest thing we've ever made is the Parker Solar Probe. It goes about 430,000 miles per hour. Sounds impressive, right? Here's the problem. At that speed, it would take roughly 7,000 years to reach Proxima Centauri. That's longer than all of recorded human history, but someone's already objecting. That's just our primitive technology! An advanced alien civilization would have way better rockets? Okay, fine, let's be generous. Let's imagine they can build a ship that goes 1/10 the speed of light. That's phenomenally fast, about 67 million miles per hour. Nothing we've built comes close. You know how long it would take to reach Proxima Centauri at that speed? 42 years. 42 years just to reach the closest star, and most stars, way farther. The average distance between stars in our neighborhood is about 5 light years. If you want to reach a star that's, say, 1,000 light years away, even at 1/10 the speed of light, you're looking at a 10,000-year journey. Think about what that means. 10,000 years ago, we were just figuring out agriculture. We didn't have writing. We didn't have cities. We were barely out of the Stone Age. And you expect a civilization to maintain a space program for 10,000 years just to send someone to one star. But this is where it gets interesting. Okay, fine. What if they go faster? What if they hit half the speed of light, or 90%? Great question. Now we run into a different nightmare. See, it's not just that going fast is hard, it's that the faster you go, the more dangerous the universe becomes. Space isn't actually empty. It's nearly empty, but not quite. There's about 1 atom per cubic centimeter floating around out there. Doesn't sound like much, right? But here's the thing. When you're traveling at a significant fraction of the speed of light, even hitting 1 atom becomes catastrophic. Let me explain. You're on a spaceship cruising at 1/10 the speed of light. You hit a single grain of sand, just a tiny speck. Know what happens? The energy from that collision, equivalent to a nuclear bomb. Not a small one, a big one. 1 grain of sand, and space is full of stuff. Micrometeoroids, dust particles, chunks of ice, debris. Any one of them could obliterate your ship if you're going fast enough. Well, just add shielding. Okay, let's talk about shielding. To protect against high-speed collisions, you'd need something thick, maybe a meter of water surrounding the entire ship, or several meters of some other dense material. You have any idea how much that weighs? And now you have to accelerate all that mass to a tenth the speed of light. Let me give you some numbers. To accelerate just 1 kilogram, about 2 pounds, to 1/10 the speed of light, requires about 450 trillion joules of energy. That's the amount of energy the entire United States consumes in about 5 seconds, for 1 kilogram. Now multiply that by the mass of your spaceship, the shielding, the life support, the fuel, the crew, everything. You're talking about more energy than the sun produces in years. How are you going to generate it? Store it? Use it? Hold on, this changes everything. To antimatter! Fusion! Something we haven't discovered yet. Let's address these one by one. Antimatter is real. We can make tiny amounts of it in particle accelerators. But to fuel an interstellar starship, you'd need to convert a significant fraction of a planet's worth of matter into energy. It's not impossible in principle, but it's not practical either. Fusion. We've been trying to make fusion work for 75 years. We still haven't built a reactor that produces more energy than it consumes. And even if we crack that, using it for rocket propulsion is a completely different problem. The energy densities are barely at the threshold of what you'd need. But what about something we haven't discovered yet? Okay, this is where we need to be very careful. People love to say this. 200 years ago, nobody knew about nuclear energy. Now we have nuclear power plants. Who knows what we'll discover next? And that's true, but here's what you need to understand about physics. In the 19th century, we didn't know about atoms, we didn't understand relativity, we didn't understand quantum mechanics. We've learned a ton since then. But here's the key, the things we've learned haven't made impossible things possible. They've confirmed that the things we thought were impossible really are impossible, just for different reasons than we originally thought. Before Einstein, people wondered if you could exceed the speed of light. Maybe if you just went fast enough. Einstein showed us. No, you can't. The speed of light isn't just a speed limit. It's woven into the fabric of space-time itself. As you approach it, you need exponentially more energy. At the speed of light, you'd need infinite energy. So that door, closed. What about warp drives? What about wormholes? I'm glad you asked. A warp drive is a beautiful idea. Instead of moving through space, you warp space itself. You compress the space in front of you, expand it behind you, and you surf on this wave of space-time. It's elegant, it's clever, and it's not even ruled out by Einstein's equations. But, and this is a massive but, to make it work, you need something called exotic matter. This is matter with negative energy density. Not zero energy, not low energy, negative energy, less than nothing. Does such a thing exist? We don't know. We've never seen it. We can write it down in equations, sure, we can say. If exotic matter exists, you could build a warp drive. But that's like saying, if I had magic beans, I could grow a beanstalk to the sky. Mathematically consistent. Yes, real. Probably not. Wormholes, same problem. To keep a wormhole open, to prevent it from collapsing the instant you create it, you need exotic matter. Lots of it. And even if you somehow made a wormhole, you'd still need to physically travel to the other end to set it up in the first place. See the problem? These aren't just advanced technologies. They require things that probably don't exist in nature. They require us to completely rewrite the fundamental laws of physics. And while I'm always willing to admit we might be wrong about something, the things we'd have to be wrong about are very fundamental. These are principles we've tested millions of times, and they work exactly as predicted every single time. But there's another problem nobody talks about, and honestly, it's the real killer. Let's say, by some miracle. You solve everything, you build a ship that can reach a decent fraction of the speed of light. You shield it, you power it, you launch it toward another star. You still have one massive problem. Time. Even if the crew experiences time dilation, where time slows down for them because they're moving so fast. From the perspective of the civilization that sent them, the journey takes centuries, maybe thousands of years. Know what happens to civilizations over thousands of years? They collapse. They change. Empires rise and fall, languages evolve, technologies become obsolete, entire cultures vanish. The people who funded your mission, long dead. The government that approved it, gone. The civilization itself might not even exist anymore. Who's gonna fund a space mission where the payoff won't arrive for 10,000 years? And here's the kicker, let's say you make it. Miracle of miracles. You arrive at another star system after centuries of travel, maybe suspended animation, which we also don't know how to do, by the way. You get there. Now what? Most likely, you find nothing. No habitable planets, or no life, but nothing intelligent, or intelligent life, but it's still at the level of bacteria, or fish. The odds of finding another civilization at roughly your level of technology, at the exact moment you arrive, astronomically small. You've spent all that effort, all that energy, all that time. For what? Now, I know what you're thinking. But if there are millions of civilizations out there, surely some of them would have tried, right? And that brings me to what I think is the real answer to Fermi's question. Let me ask you something. If you were an advanced alien civilization, and you had the resources to maybe, just maybe, send one ship to another star system at enormous cost with enormous risk and a very low probability of finding anything interesting, would you do it? Or would you stay home and use those resources for something else? This is what people miss. They think about interstellar travel in terms of, can it be done? And the answer is, maybe, in principle, if you're willing to spend unimaginable resources, accept catastrophic risk, and wait an absurd amount of time. But the real question is, should it be done? Is it worth it? And I think the answer is, probably not. If you're an advanced civilization, what do you really care about? Staying alive, staying comfortable, learning new things, exploring, yes, but maybe exploring in other ways. You can learn a lot from telescopes. You can send small, cheap robots that don't need life support. You can run simulations, explore mathematical spaces, decode the mysteries of physics. Why would you send fragile biological organisms across the galaxy when it's so breathtakingly difficult and expensive? This is sometimes called the practical mundanity hypothesis, though that's not my term, the idea. The reason we don't see aliens isn't because of some dramatic catastrophe or some great filter that wipes out civilizations. It's way more boring than that. Interstellar travel is just hard and not particularly rewarding, so nobody does it. Think about it this way. On Earth, we could build colonies at the bottom of the ocean. The deepest, darkest parts, we have the technology, but we don't. Why? Because it's hard, expensive, and not particularly useful. Space is the same thing, except multiplied by 1 billion. Okay? What about just talking to them? Communication is easier than travel, right? Yes, much easier. You don't need a ship, you just send a signal light travels at, well, the speed of light. So if there's a civilization 100 light years away and they send us a message, we'd get it in 100 years. Not bad, right? Except here's the problem. The galaxy is 100,000 light years across. If you send a signal, it takes 50,000 years to reach halfway across. Then another 50,000 years for a reply. That's a 100,000-year conversation. What civilization stays interested in a conversation for 100,000 years? And that's assuming they're even sending signals in the first place. Why would they? Broadcasting into space uses energy. It advertises your presence to the entire galaxy. And maybe, just maybe, that's dangerous. Maybe there's something out there you should be afraid of. This is the dark forest hypothesis. That civilizations stay quiet because it's safer. Or maybe. And I think this is more likely. They just don't bother. Because what's the point? You send a signal. Maybe in 1,000 years you get a reply. Maybe you don't. It's not exactly a thrilling research program. Here's what I think is really going on. I think there probably is life out there. Maybe lots of it. Maybe some of it's intelligent. Maybe some of those intelligent species develop technology. But they're all stuck, just like we're stuck. Because the distances are too great. The energies are too large. The timescales are too long. And the benefits are too small. We're all alone, not because we're the only ones who exist, but because we might as well be. We're separated by distances so vast, we can never reach each other. We're like islands in an infinite ocean, each one inhabited, each one developing its own civilization, but never able to build a bridge to another island, because the ocean is too wide, and the storms are too fierce. Is this depressing? Maybe. But I don't think so. I think it's actually kind of beautiful. Each civilization, each spark of intelligence in the universe is unique, precious. We're not going to be invaded. We're not going to be saved by wise aliens. We're not going to join some galactic federation. We're on our own. We have to solve our own problems. We have to figure out our own future. And you know what? I think that's okay. We've got a whole solar system to explore, hundreds of moons, thousands of asteroids. There's plenty to do right here in our cosmic backyard. We don't need to go to other stars to have a future in space. But people don't like this answer. They want the science fiction dream, the warp drives, the alien empires, the galactic adventures. And I get it. It's exciting, it's romantic. But science isn't about telling you what you want to hear. It's about telling you what's true, or at least what's true as far as we can figure it out. Could I be wrong? Of course, I've been wrong before. Maybe there's something about physics we don't understand. That makes interstellar travel easy. Maybe exotic matter is real. Maybe there's some quantum trick we haven't discovered yet. Maybe. But based on what we know now, based on well-tested physics, based on the actual distances, based on the energies required, the conclusion seems pretty clear. The aliens, if they exist, are staying home. And we're staying home too. We're all trapped in our own little corners of the galaxy, looking up at the stars, wondering if anyone else is out there, also looking up, also wondering. And here's the funny thing, even if I'm wrong, even if 1,000 years from now we figure out how to travel to the stars, it still won't matter for the Fermi Paradox. Because the paradox is about now. It's about the fact that the galaxy has been around for billions of years. And if interstellar travel were easy, somebody should have gotten here by now. The fact that they haven't, that tells us something important. It's not easy. It might not even be possible in any practical sense. So when people ask me, when will the aliens arrive? I tell them, they won't, they can't, not because they don't exist, but because the universe is too big. The stars are too far apart, and the laws of physics are what they are. We're alone, not because we're special, but because everyone is alone, and that's the reality check. The universe doesn't care what we want. It doesn't care about our science fiction dreams. It just is what it is, and we have to deal with it as it is, not as we wish it were. That's what physics teaches you. That's what reality teaches you. And honestly, I think dealing with reality, understanding how things actually work rather than how we wish they worked, that's way more interesting anyway. The real universe is more subtle, more complex, more surprising than any story we could make up. We just have to be willing to listen to what it's telling us. So there you have it. That's why the aliens will never arrive. Not because they hate us, not because they don't exist, not because they're hiding, but because they can't. Because space is vast, and travel is hard, and time is long, and energy is precious, because the universe, for all its wonders, has rules, and those rules, as far as we can tell, make it essentially impossible for different civilizations to ever meet. Where is everybody? They're at home, same as us. And that's where they'll stay